All right, so let's talk about sound. Um, this is kind of a very nuts and bolts explanation of what sound is. I mean, just like the title slide says, this is all about what is sound. What is it? So we'll take a look at the very basics, like the physics of sound, and then some components of how the physics come together to make a sound that we can hear. A few different kinds of sounds that we can hear. A transient sound, a pure tone, and a complex tone. Talk about all those, and put those into some terms that kind of begin to explain some things about music and speech. But mostly kind of focusing on, again, just those like very basic aspects of sound. So with that, let's move right into the sound basics. So sound is energy, basically. Um, First and foremost, it's energy, right? So when two things collide, matter, two pieces of matter, two bowling balls, two atoms, whatever, two people giving a high five to each other, whatever. Heat, light, other electromagnetic energy, and sound are all released when matter collides on Earth specifically, or any planet with an atmosphere. This would be true. Uh, I mean, of course, you know that when you do a high five, light is not released. That would be awesome. It's not true. A little bit of heat is generated because of the friction contact. There's like tiny different amounts of particles that are released when matter hits each other. Sound, of course, is released when you do a high five. That's the whole point of it. Light would just make it an even cooler thing to do. Um, but if you think about particles like in CERN, the Large Hadron Collider, we're shooting particles at each other, and what gets released is light, other particles, other electromagnetic energy, heat, sound, of course, is released in this as well. Um, so when matter hits each other, it releases energy, and that energy takes many forms. That's basically what you need to know from this: that the energy takes many forms when things are coming in contact with one another. Sound is one of those forms, but again, only on a planet with an atmosphere. So heat and light, these are all on the electromagnetic spectrum. Heat isn't necessarily it, you can kind of generate heat because of things on the electromagnetic spectrum passing through objects. It excites the molecules, so it's not exactly true to say that heat is on the electromagnetic spectrum, but it's caused by waves on the electromagnetic spectrum passing through objects like you on a hot day when the sun is beating down on you. Of course, that's ultraviolet and other visible light rays and other rays, some infrared passing through you, through your skin, bouncing off of your skin and causing heat to causing the molecules to move around and create heat. So essentially, waves on the electromagnetic spectrum, which are all photons, basically just photons with a different frequency. That's what the electromagnetic spectrum is. So photons bouncing at different frequencies are released when matter collides. That can exist anywhere. Electromagnetic energy can exist anywhere. It doesn't need a medium to exist. So you can have two particles run into each other in the middle of space where there's no surrounding uh, gases like an atmosphere. It's just a vacuum. You can have two particles hit each other in a vacuum, and electromagnetic energy is released. Radio waves, microwaves, visible light. These are all things on the electromagnetic spectrum that can be released because those waves are also particles. Those waves are also photons, so they don't need a medium because they're kind of like their own unit vibrating around and moving through space. Sound is different. Sound is not a particle on its own. Sound has to have a medium to move through I was going to say the air, but that would not be true. Sound has to have a medium to move through. It doesn't necessarily have to move through the air. Most of the time for us, it is the air. For aquatic creatures, of course, it's the water, it's the ocean or the river or the lake or whatever that they live in. Sound can move through metal and wood, rock. It can move through anything as long as it's a medium that it can move through. It just can't move through a vacuum because there's nothing to bounce around and create sound. So essentially, it has to exist within an atmosphere or travel through some sort of object. So that's what's going on with sound. One other thing I'm going to say about sound is for all these other things, we can like theoretically capture a particle and measure it. There's some Heisenberg uncertainty stuff going on there, but basically all these waves, all the electromagnetic waves can be quantized into particles, which can then be you can measure the frequency of those particles and you can figure out like this is a light wave, this is a microwave, something like that. There is no particle for sound. Sound exists in the space between the particles. Sound is how the other particles move because of the sound energy. So you can't pull out a particle and say this is a sound. What you would do is you'd find oxygen and nitrogen, in our air, and it's the air that's actually moving because of the sound. So you'd pull a thing out, and you couldn't measure it and say this is a 30 hertz tone. It's actually an oxygen molecule. So you wouldn't be able to figure out what was going on just by capturing one of the things that are moving. So sound is kind of interesting because of that. It doesn't have its own particle. It just kind of exists between things. It's never a static thing. It exists as a flowing, moving thing. It's almost like a ghost. If the sound was gone, you'd never know that it was there, right? Because there's nothing left for it to. There's nothing left. There's never anything there. It's just the way that the other molecules are moving. So that's sound. Because it's a pressure wave, so it's going to push on other molecules, it has to exist in a medium. Again, I've said it already, but just to say it again, for us it's usually air. But it doesn't have to be air. You can think of any number of situations where you can hear sound through a door, push your ear to train tracks, and you can still hear sound. But all of those use a medium. It doesn't travel through space or a vacuum because there's nothing for it to bounce off of and create a pressure wave. Okay, so let's take a little bit of a step back. Let's just talk about waves in general. What is a wave? So a wave is any disturbance or oscillation that travels through matter or space, right? So it can travel through space if it's a photon, and travel through matter if it's sound, accompanied by a transfer of energy. So sound is energy, and we're transferring energy from one place to another. Or a photon is energy, and that's moving from one place to another. So that's just any definition of a wave is just a way to transfer energy from one place to another. These ocean waves are waves. The energy is in the water itself is moving from one place to another. And then this is a picture of a sound wave. We'll talk more about sound waves, so I'm not going to go super deep into that now, but it's moving energy from one place to another. Two types of waves. One is mechanical, and one is electromagnetic. Let's talk about electromagnetic first. So we talked a lot about this in the previous slides. Electromagnetic spectrum is just all of those things that are essentially photons. So they don't require a medium to propagate because they're all photons. They can be quantized as their own particle. You can find a particle that is a like red, corresponds to like what we see as red light, which is around like 490 nanometer wave. So it's a particle that's vibrating at 490 nanometers. Or you could find a microwave particle that vibrates at a speed that is in the microwave range. So these are all electromagnetic waves. And then we have mechanical waves. All mechanical waves, and there's a few different kinds that we'll talk about, require a medium to propagate. Ocean waves are mechanical waves. They require a medium to propagate. There is no ocean wave without ocean. The water has to be moving. The water isn't the wave, but the wave is made up of the change in the water over time. It's similar to sound. There is no one sound. You can't pull anything out of the sound. But it's made up of the movement of those particles over time, whatever medium you're using. We'll say air. The movement of the oxygen molecules over time is where the sound exists. Within mechanical waves, we can break this down even further. So mechanical wave, if we want to give a definition to what a mechanical wave is, it's essentially a disturbance traveling in an elastic medium. That can be air, glass, metal, whatever. Any elastic medium. As long as it's able to vibrate, that's an elastic medium. So any disturbance traveling through that is a mechanical wave. There's two kinds of mechanical wave. So we can break this down a little bit further. There's transverse waves. And what this means is that the particles are going to move perpendicular to the direction the wave travels. So pay attention to this violin string. What happens with it as it continues to move is it's going to kind of like move down the fretboard. So if you look from like where we are right here, and then it's going to shoot further away. So you'll see it kind of like a slinky, right? If you've done the slinky thing in science class in grade school where you like wobble a slinky and you can see the wave like move away from you, that's a transverse wave. The particles of the medium are going to move perpendicular to the direction that the wave travels. So what this means is as you're looking at this string, the string is moving left to right. Like on your screen, it's moving left to right. It goes up and then down. It goes right and then it goes left. But what you can see is the motion going to the right moves down the string and then it kind of rebounds to the left. So the particles are going left to right, but the actual wave is moving forwards. Longitudinal waves, different. Longitudinal waves are going to move in the same direction that the wave is traveling. So particles are just going out. From my mouth or from this tuning fork right here, particles are moving towards the microphone, which is right here. So from my mouth, particles are moving. They're going to vibrate in this direction towards the microphone. And that's also the same direction that the sound is going. So transverse wave is like your slinky, and longitudinal wave is what a sound wave does. It moves in the same direction. Particles move in the same direction as the direction of the wave. This is just another way to visualize that same thing. Instead of a string, I've got like ocean waves here. You can see that the ocean waves are moving up and down, but the wave itself is going towards the right side of the screen. Particles go up and down, wave is moving to the right. Below that is a sound wave. What this is showing you is in the middle of a room, like a middle of a square room, we've got a speaker that is playing something, some tone. And what you can see is all of those particles are moving out, just kind of like exploding away from that sound source and going in all directions. The particles of air are being pushed in the same direction that the sound is moving. So longitudinal wave is what a sound wave is. These are vocal folds, and this is what happens when you're speaking. The vocal folds are vibrating, and this is letting out, it's creating a pressure wave, which is what sound is. Sound is a pressure wave. And so it's letting out you'll learn this if you take other classes in speech and hearing. If this is just like a physics thing that you're learning, you might not know more about this. So we're going to go just very quickly into this. But essentially what's going on is there's little pulses of air that come out between the vocal folds, which is what we're seeing here. We see it as kind of like this warbling thing. So it might look like it's moving a little bit more like a violin string. That's because of the stroboscope that's being used to allow you to see the motion of the vocal folds. But what's actually going on is air is just kind of escaping and then the vocal folds are coming back together. So we've got some air escaping, and then times when air is not escaping. And that sets up this wave on the right side of the screen. There's a molecules are moving, and then a part where they're not, and that's open, closed, open, closed. Molecules move, they don't move. Molecules move, they rebound, actually. They don't not move, they kind of rebound. Move, rebound, move, rebound. This is also called compression and rarefaction. So when the molecules are getting pushed together and moving, that's compression. And when you kind of see the molecules rebound, that's called rarefaction. And so you get this oscillatory motion from speech. That's actually jumping a little too far from where we want to be right now, because we haven't totally learned everything about a sound pressure wave. So this is kind of just like a preview of where we're going to go. Let's take a step back and talk about pressure waves. So the easiest way that we can talk about pressure waves is I want you to clap. Right? Just like that, a clap. What's going on with this clap is as you bring your hands together, you kind of are pushing air. Air gets trapped inside the hand. It gets pushed towards the other hand. When the hands meet, the air needs somewhere to go. And that creates a pressure wave. All this air that's being cupped in has to explode somewhere. That's our pressure wave. Now you can try this. I've got some other things you're going to do. By the way, I don't know where you're watching this. I want you to go ahead and do this along, like while we're talking about it. Like, go ahead and do some of these claps. If you are in a public space, you're totally going to look like a weirdo. That's fine. Just, I don't know, explain to them what you're doing or whatever. But so if you're like a high five artist, you kind of know that there's like some things that you have to do. Number one is watch the elbow to like really know where to hit the other hand. The other one is you can't go in flat-handed. You can't go in spread-handed. You have to go in a little cupped, watch the elbow, and then bam, right? So why is it good to cup the hands? Because you push more air. So that was good, and then not as good. But let's take a look at this in slow motion. So this guy, I don't know. It might be water. It really looks like he might have poured milk on his hands. And that's like, I don't know why. Why would you do that? Milk is good in coffee and cereal and not on your hands. But whatever. So here's what's going to happen is this guy's going to clap. The milk is going to explode away from his hands. The milk is basically showing what's happening to the air. So this is our pressure wave. Like this is pressure that's forcing the milk out, the milk and the air. Of course, you can't see the air, but the milk is traveling along with the air. And boom, just explodes out in a pressure wave. That's the pressure wave. Boom. Coming out like that. Pressure wave. Okay, so let's try something else. So we've already clapped and we've watched a clap. We know what a clap sounds like. That's fine. So what I want you to do is now, instead of doing the regular clap, I want you to clap only with your fingers. So like just with these parts right here. Go ahead and clap like this. It's not as forceful. It's not as loud. Why is it not as loud? Because there's not as massive of a pressure wave. This creates a large pressure wave. You're using the whole hand. You got a little bit of a cup to it. You're forcing a ton of air out. Like you don't even have to really hit that hard to get a pretty nice sound out of that. Because you've got so much air trapped in there, because the air has to go somewhere, it creates a large pressure wave. Just your fingertips, well, just your fingers, not your fingertips, that would be hard. But just your fingers doesn't allow you to grab a whole bunch of air. You can really only get what's behind the fingers, and it's not as good of a sound. Now let's try it again. Spread your fingers apart. like this and try to clap again. Nothing. I get them close to the mic and I don't even know if it registers. Yeah, you can hear it a little bit, but I can see the levels are like not going very high because of this clap. So why is this so bad? Well, okay, we get a lot of air compressed here. We get a little air compressed this way. And when you do this, there's basically no air that can be compressed. First of all, look at the shape, the overall shape of your hands when you do a regular clap. It's kind of a scoop. You're scooping air towards each other to really make it explode out of there. When you start clapping with just one finger, your finger is shaped kind of like the opposite of a scoop. It's a little aerodynamic, right? So air is just going to move around this and not get bundled up in front of it. You get two of these together and hardly anything is really happening there. But a scoop, you can really get some air inside the scoop. So what this is showing you is that the more air you've got pressing against each other creates more of a pressure wave. Pressure wave is sound. The less of a pressure wave you can make, the less of a sound you make. This is true basically in all sounds. All sounds that we're going to talk about are a pressure wave. They may not all sound like a clap, and we'll talk about why that is in a moment, but the voice that I'm using right now, this is a pressure wave as well. It's just oscillating in a frequency that creates a pitch. It's the same for a musical instrument. But this is kind of like the very beginning of a sound. It's just this like burst. It's a one-time, just a single point in time burst of sound. We call it a transient, but that's what it is. It's still a pressure wave, even if it doesn't sound like a musical instrument, which is also a pressure wave. Okay. That sound gets progressively quieter. We talked about this. Smaller contiguous surface area doesn't push as much air. I talked about that already, which means there's not as large of a pressure wave. Yeah, that's all true. I knew where I was going with that, I guess. So claps, explosions, volcanic eruptions, these are all different kinds of pressure wave. Let's take a look at some of these links that I've got here. So this is an explosion. If you want to watch the whole thing, it's pretty entertaining if you're into but who's not into explosions? Everybody loves explosions. Nobody got hurt in this, so it's fine. It's done on like a bomb. It's totally fine. But what I want you to see here is when this thing actually explodes, you can see before all the fire and the exploding stuff actually makes it onto the screen, what you see first is the pressure wave. Now, the pressure wave in an explosion, it's a transient as well, just a boom. That is the same thing as a clap. It's louder because it's pushing a lot more air. So much air that is actually what tends to do the most damage in explosions is the pressure wave. The heat, of course, if you're very close to it, can cause a lot of damage, but the heat dissipates quickly. The pressure wave continues to move. The pressure wave is what knocks down buildings. The pressure wave is what does damage to people's internal organs. And so the pressure wave is really what makes explosions so dangerous. Fire is dangerous too, but it just doesn't have as much spread. So we've got slow-mo guys already slow-mo, but let's go a little bit slower. Okay. So they're going to show us, yes, right there. In fact, I think we want to slow this down even just a little bit more. So here's an explosion from an angle. They're going to switch to a wider angle. And what I want you to watch is you're going to see kind of like a wavering little line ahead of what you might think is the explosion, like the fire and stuff. That's the pressure wave. That's sound. You actually can see the sound here because there's so much massive amount of air that's being pushed that it is bending the light through this amount of air. It's kind of like mind-boggling to think about that, but I'll point it out to you. So we're gonna switch. Okay. Now we're gonna get wider than this. Right here. Okay. So right here, right where my cursor is, you can see it. It comes out from the explosion. You'll see this just like little ripple right there. Go back if you didn't catch it. Go back and watch it again, and you can slow it down, I guess, even more because you can slow down this video. So we've taken their video. I've slowed it down. You can slow down this video. Make it even slower. Eventually, it'll just kind of like, if you make your own video, then I'll make a video about your video, and we can slow it down again. Then you can slow down my video. Then I'll slow down your video, and we'll just have a train of slowed down videos. Cool. Anyway, if you didn't see it, go back and watch it again. But that is a visible representation of the sound. Again, there's so much pressure that it's pushing the air together, and there's so much air pushed together that it's bending the light so that you can actually see where the pressure wave is. You can see the sound. This is an actual event, so this one isn't necessarily as fun to watch. People did actually die in this. I guess luckily, if you want to say luckily, this isn't like this isn't a war thing. This is just an accident. I guess that's better. I'm not sure. Honestly, not sure. But from a standpoint of looking at pressure waves, it's a great tool. So what you're going to see is this is a warehouse near a port that's on fire. Something started burning here. I think some fireworks started burning. There is fertilizer also in the warehouse. And so what happens is the fireworks start a fire. The fire makes its way over to the fertilizer that's sitting, and that triggers an explosion. So what you're seeing right now, this is smoke from the fire. There's going to be an explosion. And then you're going to see a white cloud expanding from it. That is not debris from the explosion. It's not smoke, because you'll see it just kind of like go away. What it is the pressure wave. This pressure wave is a lot stronger than the first one that we watched from Slow-Mo Guys. That was strong enough that you could actually see a ripple in the air. You could see the sound. This one's strong enough that it creates a cloud, a legitimate, honest-to-God cloud, just like these little clouds that you can see up here, because it pushes so much air. This explosion pushes so much air together that it lowers the temperature behind and allows water droplets to condense. So what you're going to see is an expanding pressure wave. So let's take a look at this. Just the first one, it's far away. We don't see much destruction. That right there, that white cloud that then goes away. We'll watch this one. You'll see the cloud evaporate. And that's because it is not smoke. Smoke wouldn't evaporate. This is a pressure wave creating a cloud. There's so much pressure that it makes a cloud. Once the pressure goes away, the cloud evaporates because you can't sustain a cloud there without the conditions created by the pressure wave. Let's look at one more example of an even larger explosion. This is a volcano explosion. And this is amazing. This is very cool. So this volcano, I want to say it was 2011, 2012, something like that, in Tonga, exploded. The sound circled the earth 3 times. And what's cool, and what we'll teach you also about sound, is how we know that the sound circled the earth 3 times. Okay, so let's take a look at what's going on here. So we're going to watch this. This animation is just going to play in a second. When I move the earth around far enough, it's just going to take over and go. So a little explanation before we go here is, here's the explosion at this red dot, and we're coming up to the time that it goes. When we get to 0, it's gonna go. So we can watch so this is talking about the shock wave from the volcano is also a pressure wave. It's a pressure wave in every sense of the word, right? It's a pressure wave like an explosion, because really close to it there's damage created by this pressure wave. It's a pressure wave in terms of sound because all the way around the world there is a sound that's created by this pressure wave. Okay, so let's get to right there. Here's when it happens. The wave circles around. That's on the exact opposite side of the world. I would love to know what that sounded like in that place in Africa. It looks like maybe around Algeria, Tunisia, something like that. Hits Tonga again, circles again, back over to like central-ish Sahara area. So I guess I was wrong about where that is. And then it comes back to Tonga. Okay, so very cool. But let me show you another thing about how we know this. Okay, so before I get too close, yeah. We're going to have to replay that animation. So if you pay attention to like the weather or anything like that, if you watch if you go to Weather Underground to look at what's going on with your weather, you may notice that a lot of people have weather stations. Maybe you have a weather station, or neighbors or parents or something like that have a weather station. And so we have like a network of weather stations here where I am in Arizona. There's a ton of weather stations, but this is not true just in Arizona. This is true across the United States, Canada, Mexico. It's also true in Japan. There's a ton of personal weather stations that are all connected to a central grid, just like the ones connected to Weather Underground. So they're reporting all the time. All the weather changes from these little weather stations are reporting back to like a mothership website like Weather Underground all the time. And one of the things that the weather stations, one of the pieces of data that the weather stations grab is barometric pressure. Barometric pressure, as a measure of what's going on in weather, changes kind of slowly, like over the course of a day, over the course of a week. Barometric pressure will change. As a storm rolls in, barometric pressure gets higher. So a storm's coming in over the course of a day, or even an hour as a storm rolls in, you'll see barometric pressure change. Barometric pressure doesn't change high and then low and then high again over the course of a few minutes. That's not barometric. Well, it is barometric pressure, but it's not barometric pressure looking at weather events. Weather events cause pressure changes on a much slower time scale. As we see something roll in, like a storm, it's on the hourly scale. As a weather system moves in, it's on the day or even week scale. But not on the minute-to-minute scale or even the second-to-second scale. That's something else. So what you're going to see is all of these dots are weather stations in Japan. And then what you're going to see is red is high pressure, blue is low pressure, and this is what happened in Japan. A wave comes across Japan. And that's in, let's look at the time scale here. So 8 p.m., then boom, right there, 8:30, it passes across the entire island of Japan in about 30 minutes across the entire island. So one personal weather station may have experienced high pressure and low pressure in 5 minutes. And so we can chart this. If we look at what's happening on every single one of these weather stations together, you can see the wave, the shock wave, the pressure wave, the sound wave from this Tonga volcano explosion pass over Japan. And this is happening globally. Across China would be next, and Korea, across Russia, across Europe, across the United States, Canada, and Mexico, just all the way across the globe. So this is how we can track these things. We can track it because it's a pressure wave. Again, such an amazing thing. So like we know, pressure waves from large events can circle the Earth or more than just one time, up to 3 times. There was a very large explosion in Krakatoa in 1883. This eruption was measured at 310 decibels. Decibels is a measure of loudness or force, the magnitude of the pressure wave. 100 miles away from this explosion, the sound was still 172 decibels. And put that into perspective for the human body, eardrums can be ruptured by sound alone at 160 decibels. So 100 miles away, if you were just standing out in a field, you could have had your eardrums ruptured by this explosion. 100 miles away. That's crazy. 100 miles away. That's like, let's say you're here in Arizona. That's like if you're in Tucson. I feel like my house is about 100 miles away from Tucson. So something could explode in Tucson and I could pop some eardrums. That is insane. And like closer than that, we don't even want to think about what happens to the body closer than 100 miles to this Krakatoa explosion. Not good stuff, is what I'll tell you about that. Oh, 2022, not 2012. So the Tonga explosion was in 2022, and that circled the Earth 3 times. This is a actual satellite image of the Tonga explosion right here. I don't think we can see the pressure wave in... Oh, you can. So let's wait for this to come around again. You can actually see the pressure wave push the ocean waves right there away from it. Pressure waves, man. That's what sound is. Okay, before we move on to move away from pressure waves and start talking about other things, this is a quick detour. If you're not interested in what's going on with condensation clouds, you can fast forward through this. But essentially what's going on is if we saw that explosion and it created a cloud, you also see this when rockets, there's one behind my head right now, but it's really cool. That was the wrong thing to move. There we go. There's one behind me right here. You can see this rocket is making a little cloud right here. The space shuttle is making a cloud. You can look at anything breaking the sound barrier is going to make a cloud, right? A little cloud on it. It's called a condensation cloud. And what it is think about a cold drink on a hot day, especially a humid day. You're going to form condensation on the outside surface of the drink. It can be in a glass like this. It could be in a can. It could be in anything. You're going to form condensation on the outside. It sweats, right? The glass is sweating. So what's going on is water vapor in the air around the glass condenses on the surface of the glass because it's a cooler surface. And so it just condenses there. What happens in these cases of explosions or fast-moving jets is there is so much air pushed ahead of whatever is moving that it creates a very low pressure area behind that wave front, behind that like pressure wave. Back here is just extraordinarily low pressure. It's so low pressure that it temporarily drops the temperature, and water vapor in the air condenses and forms a cloud inside that like area of low pressure. So what you tend to see is like here on the space shuttle, like it's not on the very front. It's kind of like forming beyond where everything is pushing through the air. And that's because in front of it is kind of like this zone of high pressure. This is the pressure wave. And then right behind the pressure wave, that's where the cloud forms. Same thing here. The pressure wave for this explosion is like right out in front of where the cloud actually is. And the cloud sits just behind the pressure wave. Same thing on a glass, right? It's not condensing in the actual glass. It's condensing just right on the outside of it. So same kind of thing. Okay, let's talk about the speed of sound. Sound is transmitted by molecules bumping into each other because it's a pressure wave. It's pushing through the air or whatever medium you're talking about. Those molecules have a speed that they can be pushed around at. In air, it's about 340 meters per second. You'll see different estimates of this, and that's because at sea level or at a little bit above sea level, or if you're in a hot place or a cold place, it's going to get pushed around a little bit. On average, it's around 340. You'll see 343. You'll also see 344. In this very slide, you'll see two different estimates of the speed of sound, but it's around 340. Density and heat, like I said, are going to impact the speed of sound, but it's around 340 meters per second. To put that into perspective, and like I said, you can use a lot of different things as mediums, as media, I guess is actually the correct way to say that. Through petroleum is 1,290 meters per second. The average speed of sound through the human body is 1,530 meters per second. Through steel and aluminum, it's around 6,000 meters per second. So if you watch a lot of Westerns, if you don't, I guess find one that's really good. And you'll see them kind of like put their ear onto train tracks to see when the train is coming. This is like how they know they want to start the train heist. Like they can hear it because the sound is going to travel through the steel faster than it is through the air. And you can hear it way before you'd hear anything in the air. That's how you know the train's about to come. You get some time to get ready, and then you like stop the train, steal everything off the train. Train heist accomplished. But in air, which is what we're usually working with, it's 340 meters per second. Like I said, there's a lot of factors that can change the speed of sound. Humidity, altitude, temperature, all these things change the speed of sound. Two of these change the density of air. Humidity and altitude are going to change the density of air. The more dense the air is, there's more molecules closer, and those can more quickly pass a pressure wave through them. Temperature is going to affect the speed of the air molecules. So you can kind of see in this little image that I have down here that in a solid, so like in metal or frozen like ice, all the molecules are like very tightly compacted. In liquid water, they're not as tightly this is actually not true for water. Water is one of the only substances that gets larger when it freezes, and that's because of the way that the H2O molecules, but anything else is going to get smaller when it becomes a solid. That's just like the way it works. So assume when we're talking about a solid that we're talking about anything that's not water, it's going to be closer together and more tightly packed. When it goes to a liquid, it's less tightly packed. Now, when we look at the difference between liquid and gas, we can talk about water because it follows the same property as everything else. You have a liquid, you have liquid water. They're condensed somewhat, like midway condensed. And they're just kind of like moving around a little bit. But when you get to a gas, the molecules are like bapping all over the place. They're moving around super fast. So if you're in a high temperature zone, they're going to move around even faster in the air than they are in a low temperature zone. And so if you have high speed in the molecules, they're going to allow a pressure wave to be transferred even more quickly. So this is why we have estimates of what the speed of sound is, because it changes with all these different qualities of the air. Qualities of the medium affect the speed of the sound. Okay, now that we've talked about all this, and we've only been looking at transients so far. Transient sounds, claps, explosions, volcanic eruptions. That's all we've been talking about. Let's move from transients into continuous sounds, because that's really the sound that we're all talking about, right? Speech, music, all that stuff. This is not the same thing as a clap. So clapping is a transient. It happens just once. There's no identifiable pitch. Even if you have a group of people clapping, it's not happening just once, but there's still no identifiable pitch to that because it's happening so slowly that each clap is an independent event. So it's not a pitch. It's just a bop. It's just that, right? There's no identifiable pitch to that. You can measure transients with, say, Audacity or Pratt. These are like audio editing applications. You can measure the frequencies that are inside of these. And what you see is that transients and clicks, things like that, are showing all frequencies at once because it's just one like explosion of sound. It's every frequency at once. It just moves the air. There's no way to really tell what the frequency is because it's just one explosion of sound. Other sounds, though, persist. Things that aren't transients persist. Vocalizations, instruments, wind whistling in leaves, like that. This all persists a little bit longer. Now, the reason why those sounds are different from transients is because they have vibration. There's oscillation, they last, and there's consistent vibration. Vibration at a consistent rate. Let's talk about vibration for a little bit. So vibration is a rhythmic oscillation of an object from one point in space to another and then back again, right? So here's the violin string that we saw before. There's a rhythmic oscillation. Rhythmic meaning it happens at a set rate. One oscillation does not have a exceedingly different time from the next oscillation. If it did, that wouldn't really be a vibration. It's movement. Vibration has to be like rhythmic. So the intervals between each new vibration, each start again vibration are the same. That's oscillatory. So you can see that happening with this violin. We've got boing, 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 boing. There's a rhythm to that, right? This is slowed way down. If it wasn't slowed way down, it would be much harder to see and you to actually hear just one consistent tone out of this. Even though you can see that it's like discrete events happening at a rate, it's going to produce one consistent tone. Let's talk about pure tones and sine waves. Maybe you've heard of sine waves. They look like this in the bottom left corner. Those are also called pure tones. So only one sound pressure wave vibrating at a consistent frequency, that's a pure tone. Just one sound pressure wave. It's got a consistent frequency, let's say like 200 hertz or 220 hertz actually, which is what I've got here. It's called a pure tone because it's just a single tone. Now, most sounds in nature are not, well, actually, I don't think there's anything in nature that really is a pure tone. It just doesn't exist. It's like something that we can make mathematically. But even when you play a pure tone, things are going to vibrate with the pure tone and add other sounds on top of it. We'll talk more about that later. There's always going to be harmonics. But for now, a pure tone is just this one sine wave. It's one pressure wave, but it's vibrating at a consistent frequency. That's a pure tone. And this is what it sounds like. It was a little short. That's a sine wave. Contrast that with like that sound of music. That's just a bass guitar. it's not the same. There's a lot more like texture to the bass guitar, do do do, and I mean it's being hit multiple times. But if you can just think about one of those notes, there's even still more texture to that than this. That's just boop. It's just one clean wave. There's no texture to it. It's just this beep, basically. Okay, we don't need to listen to all of them again, but okay. So a pure tone, what's going to happen with the pure tone is it's going to start at the baseline of where the atmospheric pressure is. Like, let's say it's in this room. There's a pressure in this room, the average pressure in this room. And you can see that represented in this graph right here by this line that goes across at 0. So this is just relative change from the average pressure in the room. The sine wave is going to start at the relative pressure, and then the pressure wave begins. So it's going to become higher, and then it's going to become negative. It's going to start becoming negative. So it's going to increase in pressure, and then it's going to start becoming negative. It's going to go into rarefaction. What that, you can think about that as the molecules, the air molecules, become more rare because they're being pushed together here, and then we go negative and they're being pulled apart. And then it's going to begin again, it's going to rebound from that rarefaction, and then the whole cycle is going to begin again. It's going to be pushed back together. It's going to start to be pulled apart. It's going to rebound to where it started, and then it's going to begin again. That's a pure tone. And again, it sounds like boop. You can have these differently. Like, you can move this around. It doesn't always have to start at 0 digitally. You can digitally start a sine wave in different places. But in the actual space, you're going to have a sine wave always, or any wave is always going to start at 0 and move positive. And the reason for that is you're not actually hearing anything. You're not starting a pressure wave with a negative. So it's always going to move positive first, and then it's going to shoot negative. It's going to come back and then begin again. If you think about that, like speaking, you start speaking or just singing a note. Like the sound comes out, and then there's going to be rebounding in there while you're speaking, but the sound has to come out first to hear it. And so you're always going to start moving in the positive direction and then come down. Again, that's not to say that you can't digitally create it where it's offset. And when we look at hearing science, we know that there's like offsets of where the wave is in its phase that help us determine where the sound is coming from. That's true. It's going to reach the ear at a different time in the phase. But at the sound source, it's always going to start moving in the positive direction first. Okay, so that's a pure tone. We heard it. Let's talk about how we're sensing these. Oh, I've got this drawn out here really quickly before we go into that. This is one cycle of the wave. Red is one cycle, and then it's going to start again. Blue is a second cycle. So each up, then down, then back to the beginning motion is one cycle. Frequency is the rate of vibration. What that means is how many cycles per unit of time. We usually talk about cycles per second with sound, and cycles per second is hertz. Frequency doesn't have to be measured in hertz. You could look at things like beats per minute. That's another like number of cycles per unit of time. Beats per minute is a way of measuring frequency. But again, usually when we're dealing with sound, we're looking at hertz, cycles per second. So how many of these cycles, this red, then blue, how many of those are happening per second? That's the frequency for sound. You can also think about it as the number of wave cycles per second. We can hear 20 hertz, 20 waves per second, to 20,000 waves per second. That's the human range of hearing. So 20 hertz to 20,000 hertz, 20 cycles per second to 20,000 cycles per second. And then this seems obvious, but I think we should touch on this, that higher frequencies, so 20,000 hertz is a higher frequency than 20, has a higher pitch. So pitch and frequency kind of like move together. 500 hertz is a higher pitch than 400 hertz, and 300 hertz is a lower pitch than 400 hertz. So ooh is a low pitch, which means it has a low frequency value. E is a high pitch, which means it has a higher frequency value. There's more cycles per second in that high E. Let's also talk about wavelength. So we know about cycles per second, like how often it's happening per a unit of time. But if there is a pressure wave that's like actually moving through the medium, through the air, again, it can be anything, but let's talk about air. Then there has to be like a length to this wave. Like there has to be space taken up by one cycle of the wave. It doesn't just exist in a packet. It exists over space. And so there's a formula for us to get to the wavelength. It's directly related to the frequency. So it's frequency equals the velocity of sound over the wavelength. So frequency equals 343 divided by wavelength. If you know the frequency, you can find the wavelength. If you know the wavelength, you can find the frequency. What this means is if you take our range of hearing, 20 hertz to 20,000 hertz, and you convert it into a wavelength, you get 17 meters to 1.7 centimeters. 20 hertz, there's a lot fewer oscillations per second. That's 17 meters. The length of that wave is 17 meters. And this is crazy. Okay, because I looked up buildings that are 17 meters high. There is a Wikipedia page for buildings that are 17 meters high. I don't know why. That seems weird to me. But it exists. You can find it. I'm not lying to you. You can go to it right now. There's multiple buildings that are 17 meters high. I don't know why this seems important to somebody, but it is. And then this is even crazier. This is a building at my campus, at ASU, the Tempe campus that I work at. There is a building on the Wikipedia page for buildings that are 17 meters high. This is one of them, and I pass by this building multiple times a week. And it's exactly 17 meters high, which means it is as tall as a 20 hertz wave is long. If I made a 20 hertz sound at the very bottom of this building, the beginning of the wave would start at the ground and the end of the wave would be at the top of the building, and that's wild to me that it exists at my campus. And then, you know what else is wild? 1.7 centimeters is the length of a 20 kilohertz wave, and that's the size of a peanut. Like the length of a peanut, not the tiny little. But so the sound that we can hear, the wavelength of the sounds that we can hear, go from the length of a peanut, not in the shell, just the actual nut, all the way to a 17-meter tall building near the statue of horses. What about sound in a space? The space changes the sound slightly. Now, I don't just mean a space like a room, although that does change the sound too, but I can also mean a space like the vocal tract that you have on you right now, or any like musical instrument also has a space that you're working with. An acoustic guitar has a space. A clarinet has a space. The space is just as important in changing the sound as the frequency itself. So every object has a resonant frequency. And this is what we call, I'm going to explain resonance in just a second. So resonance is essentially when don't have a slide just on that. So resonance is if a sound is amplified by a space. That's a resonant sound. It can also be attenuated. Some sounds are attenuated, means they get less loud because of a space. Now, resonance is usually related to the wavelength in some way. The wavelength matches the object in some way. So it's a little bit more complicated than just saying, like, oh, this bottle that I have in the bottom left corner, if the height of the bottle matches a sound's wavelength, that's going to be a resonant frequency. It's a little more complicated than that because there's like circumference of the bottle and other things, but that's a good way of thinking about it. If the size of the object matches the wavelength, that essentially explains resonance. Again, it's not exactly true. Different shapes have different resonant properties. A sphere, like your eyeball, has different resonant properties than a bottle. A bottle is actually a Helmholtz resonator, so there's just one resonant frequency that it'll resonate at. These plates down at the bottom, these are steel plates with sand sprinkled on them, and a sound is played through them. If the sound is a resonant frequency of the plate, the sand will coalesce to just one area because the plate vibrates in a very specific pattern. If it's not a resonant frequency of the plate just kind of shakes all over the place. But if you get a resonant frequency of the plate, it vibrates in a specific pattern that makes these specific shapes. These are all the same plate, no change in size. It's just a different frequency that's played through the plate, and that creates different patterns on the plate. So there's multiple frequencies that can resonate on this plate. In a glass bottle, you've really only got, well, you have a couple different modes of frequencies. One frequency, and then you can go higher, and you can get like a higher mode of frequencies. So there's like one, maybe all the way up to 3 frequencies for a glass bottle, but not as many as this plate. Up on the upper left-hand corner, you've got a room, and rooms are going to have a few different types of resonant frequencies. You've got axial, which means like there's a resonant frequency that matches the height of the room, the length of the room, the width of the room. There's resonant frequencies in all those places. Then you've got these tangential resonant frequencies where a sound might bounce from one wall to another and then back to its original place. That's a tangential resonant frequency. And then an oblique resonant frequency where it's bouncing off of multiple walls and coming back, like multiple walls and floor, and moving it kind of like an oblique angle. So you can get multiple resonant frequencies in a room depending on the shape of the room and where the sound source is located. That's also going to have an effect with the resonant frequencies. The point of this is to show you that objects and the shape of objects change the resonant properties of the sound. Now, again, what happens when we change resonant properties of a sound is if that particular frequency resonates, it's going to get louder. And if the frequency doesn't resonate, it's going to get quieter. So if you play a sound through a glass bottle that matches the resonant frequency of the glass bottle, that sound is going to get very loud. And this actually is the way that singers are able to break wine glasses, is they find the resonant frequency of the wine glass. The loudness that they're injecting into the glass is pretty loud, but then because the glass is going to amplify the loudness of the frequency that they're singing into it. This is a weird sentence. Because the glass is going to amplify the loudness, the sound pressure wave, like the magnitude of the sound pressure wave of the frequency that resonates in the glass, it's going to continue to get larger and larger, more forceful, and eventually break the glass, just because they're singing the resonant frequency. The singer isn't singing any louder to break the glass. All they're doing is consistently giving the same frequency at the same loudness. And what happens is, because it's the resonant frequency, the glass starts to get torn apart by the magnitude of the pressure wave. It just explodes. This is true for, you could do this with theoretically anything. If you played the resonant frequency into these plates down here on the bottom right loud enough, you could tear the plate apart. Which would be cool. But it would probably require a lot of power to get to that level, because wine glasses are easy to break and steel plates are not as easy to break. But everything has a resonant frequency. Every shape, every object, everything that it's made out of, there's a resonant frequency for all that. And that comes into play as well. Glass versus steel versus wood all have different resonant frequencies because of the density of the molecules. So you're running into something with that too. So it's hard for me to give you, in just this quick overview, an exact definition of how resonance is going to work in every object made out of everything, because it's different for all of them. But essentially, every cavity does have a resonant frequency, and the resonance increases the amplitude of a frequency that resonates with that cavity. If it doesn't resonate with it, it gets attenuated, which means it gets lower in amplitude, in loudness. And so that brings us into building a full sound. So once we play a lot of sounds through something and we see how those are affected by resonance, we're starting to get a full sound. So most sounds are complex tones. We talked about this, how it's really impossible to get something in nature that makes a pure tone. It just doesn't happen. Most sounds in nature are a mix of pure tones, a mix of many pure tones. In fact, there's something called the Fourier theorem, which is all sounds are a mixture of pure tones. We can use math to break down what the constituent pure tones are. And the little purple graphs that I have below both of these sounds are a Fourier breakdown of what's going on in these sounds. These are the same sounds we looked at before. This is the boop, and this is the bass guitar, which if we go further in, there's also, there we go. There's also a guitar in there. So what I've done is I've grabbed the guitar right here and this boop, and we're looking at the constituent sine waves that make up these sounds. Of course, in the boop, it's a sine wave, so there's only one thing that makes up this sound. The graph that you're looking at shows frequency along the bottom, the power of that frequency coming up the side. And so every place you see a point, like one of these like sloping up spikes, that's showing a frequency that has an amplitude to it. So that's showing what's making up that sound. This is a pure tone. It's only got one frequency, so there's only one spike, just showing that there's only power at that one frequency. The guitar, on the other hand, has a spike here, a spike here, 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 some little spikes, another tall spike here, and then more spikes all the way down. Tall one here, some little ones. So there's a lot of different spikes going on there. There's a lot of different pure tones mixed together to create the sound of that guitar. And that's a complex sound. A lot of pure tones together makes a complex sound. And again, most sounds are complex. Even something like a flute, which sounds pretty close to being a sine wave, is not exactly a sine wave. A whistle is not exactly a sine wave. There's other tones mixed into that as well. And we can break them down and see what is making up those sounds using this Fourier transform that I've got in these purple things here. So we can see what pure tones are making everything up by breaking it down. One of the things that we're going to see when we start breaking down complex sounds are harmonics. Nothing in nature produces a pure tone. Even the flute isn't a pure tone. But every sound produces harmonics. These are integer multiples of the lowest frequency. So what that means is, if the lowest frequency that I'm playing is 220 hertz, ooh, like that's the lowest frequency that I'm trying to sing. Ooh, maybe that's too low. It doesn't matter. I'm also going to get harmonics at integer multiples of that frequency. So 440 hertz is 2 times 220 hertz. 3 times 220 hertz is 660. 4 times 220 hertz is 880. 5 times 220 hertz is 1100. These are harmonics. It's going to keep going. You don't stop at 4. You get like an infinite number of harmonics that get quieter and quieter as you go. So at a certain point, it's not worth calculating all of them. But this is how harmonics work. That lowest frequency, that lowest harmonic there, 220 hertz, that's called the fundamental frequency. There's a few reasons it's called the fundamental frequency, but the biggest explanation here is if you look at these two graphs that I've got right below my head, this is showing 220 hertz, 440 hertz, 660, 880, and 1100 all together. You can see all these oscillations in there, but what you really see is this major shape that repeats. So it comes way up, a little more up, down, a little more up, then down, then way down, and then back up. And we're repeating again right here. Well, that major shape, that carrier of all that stuff that's oscillating in there, that's 220 hertz. It's the fundamental repetition package of this entire sound. That's why it's called the fundamental frequency. And below it, I've got 220 hertz, 660 hertz, and 1100 hertz. So I've pulled some of the stuff out. Actually, that's not true. I think it's 220, 440, and 880. Yeah. But I pulled some of the harmonics out. And you can see that it's still oscillating at the same 220 hertz. So it's the same carrier package. It's carrying all these sounds. The main oscillatory package is still 220 hertz. That's why it's the fundamental frequency, because we can see that that's how it's oscillating. So 220, the lowest frequency in this group, is called the fundamental frequency. We also write that as F with a little 0 next to it, F sub 0, or FO. That's the fundamental frequency, the lowest frequency in a harmonic group. And then, of course, the harmonics on top, integer multiples of that. Oh, yeah, that's a flute, which seems like a sine wave, but isn't. I don't know why I added that in. You all know what a flute sounds like. And there it is again. Okay, so we've got harmonics. We've got a fundamental frequency. We've got harmonics on top of that. An infinite number of harmonics traveling out. And then we've got all of those together. We can call that the spectral envelope. The spectral envelope is the array of different pure tones that make up a sound. So like the relative heights of all of the harmonics. The harmonics are not all at the same height. So it's not like you're going to get the fundamental and then the next one is a little bit lower and the next one's a little bit lower and the next one's a little bit lower. Some might look like that. But some might have a fundamental that's quieter and then the fourth harmonic is really high. The harmonics are all still there, but the relative height of the harmonics are different. And that's the spectral envelope. So the spectral envelope is like this overall shape of what the harmonics and the fundamental frequency are doing. Those create different sounds. That's called timbre. The spectral envelope is also called timbre, especially when you're dealing with music. Spectral envelope is a term that can be used in speech. It can be used in music in all these different places. Timbre tends to be mostly just a music term. And so timbre, if you're thinking of looking just at spectral envelope, so a pure timbre change is the difference between a trumpet and a guitar. You can hear a difference, even if they're playing the exact same note. Do that note. You can hear that one is a guitar and one is a trumpet. And the difference is the spectral envelope, the relative heights of the different harmonics, the spectral envelope, the shape of the spectral envelope. That's also true in speech. The reason why sounds different than E, or sounds different than O, it's timbre, it's differences in the spectral envelope. They're produced at the same fundamental frequency, they're produced at the same intensity. What's different is the relative, and because they're produced at the same fundamental frequency, they're going to have the same harmonics. But the relative height of those harmonics, the relative power of each of those harmonics is different because of resonance. So we're bringing it all together here. A trumpet has a different shape than a guitar, an acoustic guitar does. And because of that shape, there's different resonances. The vocal tract is different for ah than e, and because of those differences, there's different resonances. Different harmonics are going to resonate at different rates. Some are going to be much higher, some are going to be much quieter. All because of resonance. The harmonics that are a lot more powerful are called formants. So if you have if you have harmonics that are particularly strong, particularly loud relative to the other ones, those are called formants. All sounds can have formants. They're particularly useful in speech because we look at the formants, especially the first three formants, to determine differences in all of our vowels and semivowels and diphthongs, all of these different phonemes. But we also use them in music too. And so this picture that I've got below the text here is showing formant frequencies in old classical Italian violins and also in the human voice. So there's violin made by Amati. This is like a fancy, it's not a Stradivarius, but it's basically just as crazy as one. We've just all heard of Stradivarius. None of us has heard of Amati or DeSalo. But these are like really well known if you're in the biz. Violins. So Amati and DeSalo, those are on the top. Amati's on the left, DeSalo's on the right. And then what we've got down below is a male vocal tract and a female vocal tract. So these are like vocalizing the same phoneme, the same vowel phoneme. And the violins are playing. And you can see that what's being measured here are the formants. We can see formants in both speech and music. And essentially, just again to reiterate, the formants are the harmonics that are particularly loud, the ones that have been amplified by the resonant cavities. And what this is showing us is that the Amati violin has the same resonant characteristic as a male voice, and the DeSalo violin has the same resonant characteristics of a female voice. And so they're kind of modeled after these different singing voices so that you might use one violin versus the other in a certain piece if you wanted to give it the sound of a man or a woman singing. So you can have formants in all the different areas. Formants just mean high amplified harmonics. Which harmonics are amplified? The ones that are amplified, those are formants. Those are ones that you should pay attention to because they show resonance in the sound tract. I was going to say the vocal tract, but that's not exactly true. They show resonance in the cavity that the sound is coming through. So formants, very important to know for looking at speech and also music. So lastly, let's go back to sound. So sound here on Earth is all around us. Everything's making sound all the time. You can have something making a small sound, but there's going to be harmonics on top of that. The air is just going to oscillate. The material that it's made out of is going to oscillate. There's going to be harmonics because of one small little sound. Also, sounds are going to resonate because of different cavities, because of things that the shape of things, what they're made out of, they're going to resonate. In fact, the next time you're in your shower, try to find the resonant frequency of your shower. Just move up and down a musical scale as you're in there, and you'll find one that's particularly loud in your shower. Don't change your loudness while you're singing, but you'll find one that just gets really loud in the shower. That's the resonant frequency of your shower. So it's all around us. Sound is hard to escape. There's things making sound all the time because anything moving up against something else is disturbing the air and creating a sound pressure wave that's then going to move through the air and hit your ears. Remember how I said that sound needed a medium? This is true. Sound does need a medium. And if you're a human and you're listening to things that are between 20 hertz and 20,000 hertz, you definitely need a medium around you. But the universe can also be a medium. The universe has stuff in it, right? It's got galaxies, it's got nebula, it's got all this stuff. It can be a medium, not for something that we can hear, not something that's between the size of a peanut and the size of a 17-meter building. But for much lower frequencies, the universe can be a medium. And there's actually something called baryon acoustic oscillations. These are ultra low frequency vibrations from the formation of the universe that are still moving things around in the universe right now. We can detect them with the James Webb Space Telescope. We can look at these movements. This graph down below is kind of showing where galaxies have been pushed together. There's more galaxies in these little rings than there are outside of these rings. And the reason for that is because of resonances in the universe, because of sound waves moving in the universe. This is doing the same thing as those plates that I showed you when we were talking about resonance. The universe is doing the same thing as those plates. There's places where resonance is pushing things together. On the plates, it's sand. In the universe, it's entire galaxies with us in it. So sound is actually everywhere. It is all around you. It's moving the universe that we're all in right now. So, pretty crazy. That's sound. In some ways, this was a lot of information. In other ways, this is like just barely scratching the surface of everything that sound has. But hopefully this gives you a better understanding of what sound is and how it moves in the world.